Hello everyone, my name is Yazid and I'm the group leader, and these are my group members.
And I'm Yusuf.
Hello, my name is Mohammed Usman.
Hi everyone, I'm Yaqut.
Hello everyone, I'm Zora.
And today we'll be talking about application of differentiation.
Before we start, there are some few things that need to be stated. There are two parts in this question. Solve each in your math workbook. Remember to show all your working, and the answers will be showed at the end of the presentation. So the question is, a local company designs a conical water funnel for industrial use. The funnel has a circular base with a radius of 10 centimeter and a height of 10 centimeters too. So you were given this in the example. Placed with its tip pointing downwards, during testing, water is poured into the funnel at a constant rate of 4 pi centimeter cube per second. So we were given the dv over dt, which equals to 4 pi. As a part of the team's task in the product development department, you are to analyze the rate of change in the depth of water inside the funnel during filling. So part A, calculate the rate at which the depth of water is increasing in the funnel when the current depth of water is 5 centimeters. Part B, determine the rate of increase in the depth of water in the funnel 4.5 seconds after the pouring has started. So we were given T, which equals to 4.5.
So here are two hints we can use before we start answering. First, we're given the formula of the volume, which is 1 over 3 pi r squared h. And we also need to know that we need to express r in terms of h before we start differentiating. So now it's time for answers. And for question A, the first step is to find r in terms of h. We have r as 10 and we have h as 20. So we're going to use the ratio r over h is equal to 10 over 20, which is going to be half. So r is 1 over 2h. For the second step, we're given the volume formula, which is 1 over 3 pi r squared h. We're going to sub in r that we found in the first step. So we're going to have the equation 1 over 3 pi into 1 over 2 h squared into h. We're going to have v as pi over 12 h cubed. And for step 3 and the final step, we're going to differentiate v that we found in step 2, which is pi over 12 h cubed. So dv over dt is going to be equal to pi over 12 3h squared times dh over dt. We're given dv over dt is equal to 4 pi from the question. Also h is given in the question to be 5. So we're going to sub in these values, and 4 pi is going to be equal to pi over 12 3 into h squared times dh over dt. We're going to rearrange the equation to find dh over dt, which is going to be 0.64 centimeter per second.
Okay. So now we'll be talking about step B. So in part B, step 1. So we have the equation volume is equals to rate multiplied by time. We got this equation back in high school. Easy stuff. You must know this. Okay. So in the previous question, my group mate Yaqut talked about the rate being equal to dv over dt, as you can see here. So we just substitute dv over dt with the rate to get v is equals to dv over dt multiplied by t, which is time. So in the question, it says that the rate was equals to 4 pi and the time taken was 4.5 seconds. So if you substitute it into the formula, you will be getting v is equals to 4 pi multiplied by 4.5. Plug it into your calculator and you're going to get 18 pi centimeter cubed. And that's going to be our volume. Okay. So now, step 2. V is equals to... Oh, sorry. I accidentally wrote the line. So, In step 2, V is equals to pi over 12 h cubed, which we got from part A, if you can recall that, which you should. So we found that V is equals to 18 pi, as you can see here, from the step 1. So we're gonna put it into the equation. So 18 pi will become equals to pi over 12 h cubed, because we're trying to find h, or the depth. So h, if you like rearrange the formula and make h the subject, you're gonna get h is equals to cube root 18 pi divided by 12. So if you like plug it into your calculator, you're gonna get h is equals to 6. So now, on to step 3 and the final step of this question. So from part A, you should also remember the equation dv over dt is equals to pi divided by 12 3h squared multiplied by dh over dt. So again, we use dv over dt, which is equals to 4 pi. And h, the value we got from step 2, is equals to 6 centimeters cube. Or 6 centimeters. So you plug it into the equation and you get dv over dt is equals to 4 pi. Pi divided by 12 multiplied by 3, and the h you switch it into 6. So 3 multiplied by 6 squared. 6 squared is 36. 36 multiplied by 3 is equals to 118. Right? So 4 pi is equals to pi divided by 12 multiplied by 118 multiplied by dh over dt. And since the question asked us to find the dh over dt, we're going to make it the subject, and then we're going to do 4 pi divided by 9 pi, which is just another way of simplifying it. So the final answer will be 0.44. I hope you got the same value as this, and if you didn't, it's fine. You can try again. Thank you.
Why is differentiation important? When pouring in water into a funnel, the depth of the water doesn't increase at constant rate. This is because the shape of the funnel causes the radius to increase with height, meaning that as more liquid is added, the volume grows faster near the top. As a result, even though more liquid is being poured in, the depth increases more slowly. Engineers use differentiation to calculate how the depth changes over time, allowing machines in automating systems to adjust flow rates or stop pouring at the exact right moment. This ensures efficiency, accuracy, and safety in automated filling systems.
So today I will talking about the real-life applications of physics and fluid dynamics. In industrial fluid filling systems. These systems are extremely important in industries we use and rely on every day, such as food and beverage production, chemical processing, automotive services, and pharmaceutical manufacturing. At first glance, pouring liquid into a container might seem simple, but at the industrial scale, this process becomes much more complex and must be done with extreme accuracy. In these industries, liquids must be transferred into containers in a clean, fast, and efficient way. That's where automated fluid filling systems come in. These systems are designed to ensure every container is filled with the correct volume, down to the last millimeter. If the filling is too much, it leads to overfilling and spillage. If it's too little, the product doesn't meet quality standards. This could cause problems with customers or even violate safety regulations, especially for pharmaceutical products where the right dosage is critical. Here's where physics comes to play. Most of these systems use conical funnels,
which are wide at the top and narrow at the bottom, so help guide the liquid into the containers. When a liquid is poured into a conical funnel, the rate at which the liquid level rises is not constant. At the narrow bottom of the funnel, the water level rises quickly. As the funnel gets wider towards the top, the same amount of liquid causes the level to rise more slowly. This happens because the surface area increases as you move upwards. Engineers and designers have to understand this behavior when building these machines, especially when programming them to stop filling at the right moment. There are many examples of these systems in actions, such as beverage bottling lines are used to fill soda, juice, or water bottles quickly and precisely. In pharmaceutical factories, the sterile liquid medicine is filled into glass bottles. In cosmetics industry, lotions and creams are poured into tubes and jars using viscosity paste fillers. In the automotive world, even something as simple as pouring oil into an engine uses the same funnel principle. And on a larger scale, factories use advanced automated funnels and pistons to fill hundreds of containers per minute. If you if you've poured if you've poured into a bottle liquid into a bottle without a funnel and spilled it, you already know how tricky it can be. Now imagine doing that hundreds of times in a minute without making a mess. That's the job of these machines. They need to be perfectly timed and precisely controlled to avoid waste spillage or damage. In a conclusion, industrial fluid filling systems may seem simple, but they are a perfect example of real life physics and technology working together. Concepts like flow rate, pressure, geometry, and volume control are all used to design efficient, safe, and reliable filling processes. It's a great reminder that even basic scientific principles can have powerful applications in the real world. As you can see, funnel machines are being used to fill bottles of soap, and these are for medicines, and the engine of a car being filled with oil, and this is the viscosity paste filling. Thank you.